3 or 4, I guess, for mean, medium, mode, mid-range, right? You should have done all those in the first section here. And properties of all these as you go through them. We kind of worked on all the concepts, the mean, medium, mode. And you know how to do them on the calculator? Find them?
Oh, we know how to do the
Like
mean
taking
and
the
the
lessons.
median.
I mean, do you know how to put like a list of values in and
Yeah.
find them all?
Austin showed us.
Okay.
Or some of us, I don't know if everyone knows.
How about? And what do you know?
Yeah.
I kind of
Maybe we should go over it.
Yeah, we should go over
I can
it.
go over that in a little bit here. And it's not hard to do. We'll talk about the formulas as you go too here. Let's talk about this and I'll show you how to do it in the calculator. Properties of the mean, you know this, it uses all data values. All the values in this range. Varies less than the mean and mode. You know, the median and mode can vary a lot as you go through here. Used in computing other statistics such as variance. Mean and mode is not used very often, besides finding the middle value. Mean is used in many other formulas. So that's probably one of the most unique things about this. Unique, usually not one of the data values. When we do mode, it is one of the data values. Median could be, doesn't have to be. If it's split between two values, it could be in between. Mean doesn't have to be. I kind of curious what you think of this. Cannot be used in open-ended classes. In other words, if you did a table of frequency where it's like your values go on, and then the last class from 6 and above, you know what I mean? It cannot use on open-ended classes. You can't use there. And affected extremely high or low values called outliers. So in other words, outliers will affect the mean. You can either move it up or move it down. The median is the midpoint. Used when necessary to find out whether the data falls in the upper or lower half of the distribution. In other words, median, for 50% of the values are above, 50% of the values are below, right? Median. Can be used for open-ended distribution. So it can be used if the values are going out forever. And is affected less than the mean by extremely high and low values. It is still affected. The mean can be still affected, but it's affected less. Mode, less things here, used when typical case is desired. In other words, once you just simply know which one happens more often. The easiest average to compute can be used with nominal data. What's that?
Like colors.
Colors and types of cars that can be used. Mode can use that. The other two can't. Not always unique or may not exist. What I mean by may not exist is a mode does not exist if everything occurs once. Mid-range, again, easy to compute, gives the midpoint, and it is affected by extremely high and low values of data set. So in other words, that outlier will affect the mid-range quite a bit. What is the mid-range? High plus low divided by 2, right? So if I had an outlier way out here and I had high plus low divided by 2, that's going to move it way out, right? It's not going to be a very good estimate of the middle as you go through. Distributions, you can look at this, positively skewed, and little things down here. Let's start down here. If it's a bell-shaped curve, all of them are the same. All of them are right in the middle. If it is skewed, positively skewed or right skewed going down to the right, you'll notice that the mean goes that way. It's on one side, median's in the middle, and mode's on the one side. And if it's left skewed the other way, the mean is always with the skew. That's how I always remember it. The mean is always with the skew on the side. It changes the mean. So depends on where your value is. So if they'll give you a graph and ask you where about would the mean be, which one would be higher? Mean, median, mode. If your graph is skewed, you should be able to say, if I give you a graph like this, you'd say the mean is higher than the mode. The skewed graph. And okay, let's take your calculators if you have calculators. Everybody have one?
That's a lot.
You can grab one on the back cover if you want to, or in the case back there. I was just getting locked up for speech today.
Yeah, those are some other colors.
I would really lock it up because you're talking.
Probably
I don't
got
have
a top on
either.
my locker.
I know I don't either, but they'll just be on
What if I
tomorrow
was
morning.
to, Oh,
I'm
so
gonna
they
see
take
all
all
your
your
But
books.
books?
Kelly, you know what,
Outside
it's gonna,
one.
someone will be stupid enough to unpatch it, so.
Probably, and then I'll go in the morning.
Did someone else pencil yours earlier this week too?
Who
That's
does
because
all
your lockers
that?
are behind
There was a lot of lockers unpatched.
Yeah, it was like all of them.
Okay.
Mine was-
List of spreadsheets.
Everyone.
I should get that somebody.
Pencil.
No, I've been.
Oh, I usually pick on somebody with their lockers. Like last year, I can't remember who it was last year, I went out and duct taped their locker shut, totally, no duct tape.
Duct tape their lockers.
Do it.
For why? That's actually pretty.
They were actually kind of mean.
They were mad.
They came back and took my whole recycling bin and shredded it, and spread it on the whole floor, my whole floor was
What?
equally white.
Alright, that's
Are you
what
serious?
was this?
It was last year, so.
And I missed it?
I knew
Oh, it was.
Who was it? I can't, we didn't put, and then I took her purse and still took that and hit that.
This
She
is
could
pretty
find
funny. It was a student?
I feel like it might be Victoria Tyson if she's. was
Yeah,
that
I'm
bad.
thinking Vicky too.
I like the shredded idea.
Yeah, I couldn't believe it. I walked in my room, went for lunch, I came back and my whole floor was white. I mean, they had the whole floor completely covered with paper.
You know how long that would have taken?
Yeah, I think they had a lot of help. So,
Where was I? Like,
Yeah.
what?
Why did I miss that?
so it was last year, I'm pretty sure, so.
Yeah, man, we would've had Colin right after,
So,
pretty close to that, so.
yeah, it was
Then came
interesting.
here.
Okay, values, how to do this in the calculator, I'm gonna explain a few things on the list here. Let's just pick some values up. I usually label my list as you go through here, X. We'll use that second line later on this year. Let's just type some numbers in, let's say 3, 6, 9, 5, I don't care what you type in. Okay, got a lot of numbers. I don't care how many numbers, I just picked a whole bunch of numbers. Go under menu. Statistics calculations. And you're gonna get used to this, but because actually, I'm just gonna go back a second here. All these are distributions. You're gonna have a lot of distributions, you got confidence intervals, and we have other tests. We're gonna be using every single one of those,
Distribution?
all those this year.
Does it do a frequency distribution?
And what we're gonna do is a linear regression. No, sorry, one variable statistics, not linear regression. One variable statistics. We only have one list. Number of lists is 1. And I call my X list X. And the result, this just tells me where my result's gonna go. If I put my list in the A column, this is gonna go in B column. Now, if you remember some of this stuff, what's the first one?
You're mean.
Mean. X bar is your mean. First one's your mean. Second one,
Is that the sum of all the
sum of all the numbers. The sum of all the numbers added up. So I took my first list, that would be all the numbers added up. Okay? Sum of X squared.
numbers? Sum of your numbers.
Yep, sum of my numbers squared. You're gonna use that in a lot of formulas. It's taking every number and squaring it and then adding them up.
Oh, I don't get it. So we'll take 3 squared,
Yep, you would take that.
6 squared.
Yep, you would square each of these numbers and then add them up. That's what that
Oh
would
yeah,
be.
don't we use that when we do the or the,
Variance.
yeah.
You use that in variance. Okay?
um,
Keep going here. Okay, S of X, sigma X. S of X is your standard deviation sample. Sigma X is your population standard deviation. If you look ahead a little bit, there's 2 different formulas. One's for a sample, one's for a population. They'll give you both here. You know, so a little different.
How do we have a-
Symbol, the O.
How do we have a population and a sample when we're just using these numbers?
If what you know, they give you both is now as this. You don't know if this is a population or sample, right? So therefore, if you know if it's a sample, then you'd use this one.
Oh,
And
okay.
if you know it's a population, you use the bottom one. And what was your question?
And then I just said I remember the little symbol with the O.
Yeah, sigma. sigma x is the population, that's all sigma. Letters, actually, that's a good point to make. A lot of times when you deal with letters, you'll notice that like S and all that kind of stuff, we usually are dealing with samples. When we get into the Greek letters, like here, sigma, and later on we'll use rho and all these other symbols, that means you're dealing with a population. So letters usually mean sample. And
Number of times.
number of values in your list. Okay, MINX is easy to know. Minimum value. Q1, first quartile. If you remember boxing whisker plots, first quartile, second quartile, third quartile. Median, max, middle value, and median. Quartile 3 is our third quartile, max. Sum of SSX, sum of the squares of differences. We'll talk about that. What that is if I took my mean, and we use this in formulas, if I took my mean of my values, okay, and subtracted each value for the mean. Okay, in other words, let's say my mean on this one was what? 5.77, okay? If I took 3 minus this, got a value, 6 minus this, 9 minus this, 5, each one like that, right? And then I squared each of those terms, and then I add them up. Oops. That's what I get.
What do we use that number for?
One of the formulas, if you look at your formula sheet, you should have a formula sheet in front of you, right? I think every book had one, right?
Who has time to think up all these equations?
Well, like, I don't know why we need to square everything. Like, what does that help us in real life for?
Okay, why would you square everything? Okay, when you look at the differences, okay, that's a good point. Let me see if I can find the formula right now. You'll see a lot of the formulas, but I don't see the one looking for right now. Why we square them is because, let's talk about regression line. You know what a regression line is?
Yeah.
Okay, if I look at a regression line, when we do statistics, what happens a lot of times is, let's say, here's my points. And I drew my regression line like this. Is that a good line? Okay, why? You're near all the points, okay? What a regression line does, and this is what happens in statistics, the error above and the error below would be approximately the same. So like this error would offset this error, right? If you think the error above being positive, the error below being negative, right?
Okay.
And if I went like this all the way through, what would happen? Error above and error below would be equal, right?
Yeah,
And it would equal always 0. So when I think about why you're squaring it, think about this one. If I took my mean, I took each value minus the mean. Mean means middle, right?
Oh, yeah.
Some will be above and some will be below. What is it always going to equal? 0. If it's always equaling 0, does it help us any? No. So therefore, what we said to do is, okay, let's square it. It's never going to equal 0. But what do we want to happen? Get very close to 0, right? It's going to be positive always because we're squaring the numbers. And we want that number to be as small as possible.
So we kind of find out how far the points are off.
Yeah. You know, and we square it, because otherwise it's always going to equal 0, and that's not going to help us. And that's kind of why we square it, if that makes sense.
Yeah.
So, I mean, it is a concept where, and to answer Matthew's question, who thought a lot of these formulas? I don't. A lot of these formulas, if you look at that formula sheet, there is some nasty formulas on here. And I remember proving them in college, but I could never prove them again right now. You know, and so, I mean, these are not nice. I say this is I remember proving the variance and ones and all that kind of stuff. They're not nice to work with. So, in the first section, and I'll get to some end of class now, so I can try and answer any questions you have. On the first section, you deal with mean, median, and mode, right? And mid-range. Now, section 2 is the other ones. Variability. There's a lot of different variabilities. And a lot of different rules we're going to use. And I think a lot of these we dealt with before. We dealt with range, right? And we dealt with variance and standard deviation. coefficient of
Chevy
variation.
sheds, I remember that.
Was that?
The Chevy sheds, that one.
Yep, Chevyshev's theorem, and the empirical rule.
We did that there.
We did the empirical rule. And the empirical rule kind of goes back to the normal curve. That's the empirical rule. Chebyshev's theorem is one where it's not normal. It's a little less forgiving. Coefficient of variation tells you how confident your values are. Standard deviation is not hard to find. Standard deviation is simply the square root of variance. So if you can find variance, you found standard deviation. Or vice versa, if you found standard deviation, you found variance. And range, max minus thing. That's the easiest one. Which one's the least used? Which one tells you the least amount of data? The range. Range is max minus min, that doesn't tell us anything. And like I said, range is the difference between the highest and lowest values of the data set. It really doesn't. It tells you how spread out your data set is, right? But if you have an outlier, it's not going to help you a whole lot as you go through here, so it's not the best value to use as you go through. And I'm not going to do example on range. I think you guys can figure out range. Maybe this is an example. 2 experimental brands of outdoor paint are tested to see how long each will last before fading. 6 cans of each brand constitute a small population. The results in months are shown. Find the mean and the range of each group. Let's just deal with the range. I mean, this is not hard. Group A, highest value is 6, lowest value is 10, so the range is 50. The next group is 45 and 25, and so the range is 20, okay? Which is better, right? More consistent, okay? B says, B is 20 away, and you say more consistent, okay? Why not A?
It's too great.
It could be variable, but look at the vein. We had lasted 60 and 50 months, right? The other brand didn't have any of them last 60 or 50, right?
It's a sample, so it's not, it can change very easily.
Could change very easily.
Skewed sample.
Good sample. This is where we're leading to. Why would one be better than the other?
What if your paint was in Antarctica?
We don't look at scenarios like that one. But what I would get you to think is think differently. You know, you can look at these values and say, okay, maybe the average of this. If I found the average here real quickly, it's 180, 210 divided by 60 is all 35, right? Right around 35. If I found the average of the other one here is 110, 150, 210, 35. Both have the same average. Both are averaged the same, meaning it's the same. You know, now, which one's a better model? You probably, like Parsi said, this is less variable. On average, you're going to get probably a 35 on here, for sure, right? On this model, yeah, the average is 35, but what might happen? You could get down as low as 10, but you could get as high as 60. And then we go on to Peterson's comment, which was,
You don't know where it's being used or what it's being used on.
and we don't know a small sample size, right? A small sample size. Is it significant? Is the difference significant? So we're going to look at different options here as you go through. I don't know why my picture showed up that way. Now, measure of variance. Now, this is where I wanted to get to today. Variance. Variance is the average of the squares of the distance each value is from the mean. Okay. Further comment. Let's read the sentence. The average of the square of the distance each value is from the mean. Average would be. Divide them up and divide by how many there is, right? Okay. The average of the square of the distances, each value is from the mean. So in other words, take each value. We just talked about that summit SSX on that calculator, right? It means take your average of your values, right? Take each value minus that average. Square it. Add it up and divide by how many values there are.
So that's the SSX is the variance.
That's the sum of the square distances. We still have to divide how many values there are. Standard deviation is the square root of the variance. And this is key right here. The standard deviation is the measure of how spread out your data is. The smaller the value, the closer together your values are. So if I had a standard deviation of 1 and I had a standard deviation, okay, let's say I gave a test and it said the average of my calc test was 85 with a standard deviation of 1. Okay. Plus or minus 1. And my stats test, the average of the test was a 90 with a standard deviation of 6, plus or minus 6. Which one did better? Now the average is 6, but there's a lot more lower scores on the stats than in calc. Calc, the range of values are very close together. Now the formulas for these, real quickly, I believe is on the coming up. Okay, let's talk about this first. We use uses of variance and standard deviation to determine how spread out the data is, to determine the consistency of a variable, to determine the number of data values that fall within a specific interval. This is, you probably, somebody said Chebyshev theorem. That's what we did here. What percent of values fall within an interval? That's what we use variance for. And use then one of the types of statistics. What are the two types of statistics? Inferential. There's 2 on the test. I was interested in reading those 2. There's a lot of ways how people spell those words. I can tell you spell check in English papers. So 2 formulas. Population. Notice this formula. You take an average value, and this is what I talk about with population. If you look at it, we're using Greek letters. Population variance, sigma squared. Population mean, x minus your mean squared. This symbol is your Riemann sum, that means sum of the values.
What's that other upside down H thing?
That's your mu. It's called mu. And that means your population mean. If I write mu down, that means you have your mean, and that's your population mean, not your sample. Notice here we got capital N on the bottom. Capital N means the total number of samples that we're dealing with a population. Again, this symbol here, remember that means Riemann sum, it means add them up. Add them up values. Notice the standard deviation on the bottom. Standard deviation is sum of x minus x mu squared. It's the same formula you got for variance, but just take the square root.
What was X?
X is your set of values. When we do this, I mean, a sum means you have to take each x value, subtract it. Okay. So we'll do one of those examples in a second here. Okay, and let's find one in the book here. Let's see here. Let's do one in the book. So let's take your books. What's homework? Let's do your homework, actually. Section 3.2, which one you had to do for homework?
I think
Oh, 3.3, actually, sorry.
2, 1, 2, 5, 7, 10, 19, 28, 32, 37, and 43.
Let's do number 7. Oh, actually, hang on. Let's do number 7, but we're going to treat it as a population. We don't say sample. Okay. So here it says the number of incidents where police are needed for a sample of 10 schools in Allegheny County. Explain the answer. So it does say sample, so we should use a sample, but we're going to do population in this one. What I want you to do, the first thing is I want you to find the means. So add them up, divide by how many values there are. 13.3. For curiosity's sake, rule of thumb when rounding, I think this is here. Rounding, finance should be rounded one more decimal place in the original data. You'll notice all my data is two whole numbers. So whatever the data is, you always round it one more place than the original data. So you notice I rounded my mean on here to 13.3. Okay? Now to find that this is my, and for this we're dealing with population, so this would be my mu. We're going to deal with population, assume it's population. So now what we're going to do on the column reference here is, if you remember the formula was this. It was the sum, that was not the symbol, sum of x minus mu squared divided by n, correct? For variance. So what we need to do next is take x minus mu. X is my list of numbers. So what we're going to do is take every number and subtract the mean from it. If you want to, we're going to do it. You can do it in two columns, and then the next column after that would be x minus mu squared. So you can square them at the same time if you want to. So I'm just going to write it down here. So we're going to have 7 minus 13.3. Then we're going to square it to get that answer. Follow me? And then 37 minus 13.3. 3 minus 13.3. And you would have to square each value. Add up that column. Okay. Now, if you look at the formula, it says sum of the x minus mu squared, right? That's what this is. That's what that is.
So is that our variance?
And our variance, that's the top part. So really, we're gonna have 2292.10, so I should say sigma squared. 22.92 over, how many values do we have? 10, so over 10. So our variance on here is, if I divide that by 10, 229.210. If I divide by 10. And our standard deviation would be, take the square root of that value.
47. Wait, what'd you say we're down to?
You better not get 47, 15. To square root of this number, not the square root of that big number. 15 point what?
How many does
It's always one more than the original data, so
it? 15.1.
15.1. Now this one probably should be brought up to 229.2. Always one more than the data, right? So we got, our variance is 229.2, our sigma is 15.1. Is it a very big standard deviation?
Yes.
This is very big.
It's bigger than
Yeah, so this is very spread out numbers. So 15 is you're usually looking for like 5 or 6 or 3 or something like that. 15 is a very large number. Now, it depends on the data too. Some of your data is very large too. So, questions on that? Now, if you look at this as you go through, we did the orthopane here. Sample is very similar. Formula. Sample is on here. If you notice, sample variance is same formula. Now you notice on here we got letters now. X bar, that's your sample variable. Sample mean. Sorry. A little different formula. It means the same thing. There ain't much difference in what we're doing here. This is your sample mean. Lowercase letters deal with samples. Lowercase letters deal with samples. Notice the formula though on sample though. We're not going to divide by n. Divide by n minus 1. When we get into the understanding is the degrees of freedom. And why is n minus 1 is, I don't know if this book does a very good job of talking about it, and I can't, it's hard to explain. What it is when you take a sample of a population, can you assume it's exact as the population? No. And what happens here is to make it so we have a little leeway to work with, what they say is we're going to take 1 degree away. That gives us the degree to say that this is very close to the population. Okay? We deal with a sample. And so therefore that's why we divide by 1 less than that. So you have to remember, that's why when you're doing these problems, you have to determine, is it a sample, is it a population? If they tell you it's a sample, you're going to have to use a sample variance as standard deviation. If it's a population, you're going to use the other one.
Do we have to use our formula sheets on tests?
Yep. Yeah, I do use those sheets all the
Are these on it?
time. I believe those are
Yeah, standard deviation.
standard deviation, population.
For sample, but theirs looks weird.
There's a little different. There's a little different. There's a shortcut method. And I don't like the shortcut method, actually. I think they use the shortcut method on here. And like I said, their formula looks longer than the shortcut method.
Yeah.
And so, I'm not going to go through, do I have to go through another sample? There's not much difference on theirs. Measure of variance of standard deviation sample competition model is mathematically equivalent to the theoretical formula. Saves time when calculated by hand, does not use the mean. Is more accurate when the mean has been rounded. So what you have here is, this is the formula they have in your sheet. Sample variance. Like I said, I don't know, I like using the more formula they have right now, and I would probably stay with that one. It's not, Here you have to take, you don't use the mean on this formula. It gives you the kind of the same, it gives you the same answer. You just sum your x squared, the sum of x squares, and all this other stuff. It's exactly the same formula, but it's a little more work, I think, than just subtracting. Notice though, too, when you did it on the calculator, let's take your value, start a new document real quick. New document, no. Listed spreadsheets, I'm gonna label this, and X. So no, list the values off from that problem again. 7 was the first one, right? What's the second one? 37? 3?
8,
48?
11, 6, 0, and 3.
Okay. Now if I go menu statistics, one variable statistics, say okay, X, okay. I have my values. My mean, you notice right away, 13.3. Usually the calculator will do the rounding for you on here. You could use the shortcut method if you have your sum of x's and sum of x squared is real easy. But if you go down here, what did we get for our standard deviation? 15.1. You'll notice the population one was the one we did, right? The population here is 15.1397. We'll be pretty close. It's right there. If we go down on the bottom list down here, what was our sum of our squares? The 2,292.10, correct? That's that value that we added up when we subtracted all of them. So I mean, if I have you do one by hand on the test and using this formula, you still have your calculators in front of you and say, okay, I didn't get the same answer. You can kind of check your numbers a little bit. If you know that you squared each value and added it up and it doesn't equal this value, you know your squares are off a little bit. Okay? You typed the number in wrong a little bit. So this kind of gives you where your values should be. Any questions on that? So that's where the numbers all come from. And another example. We're going to kind of cruise through some of these examples. Coefficient of variation is the standard deviation divided by the mean expressed as a percentage. It tells you which one's more variable. So if we take the standard deviation divided by the mean, it tells you if it's more variable or not. It says which grade is better, which one's more spread out. Okay. You would rather have a less spread out one with percentage of variables. For example, I think they have a problem here. Let's go here. The mean number of sales of cars over a 3-month period is 87 with a standard deviation of 5. The mean commission is 5,225 and the standard deviation is 773. Compare the variations of the two. So why couldn't we do a compare the standard deviations? Because they represent two different things, correct? One represents the standard deviation of the number of sales of cars, right? And the other one represents the price of the cars. One represents how many were sold, and one represents price. So you can't compare the two that way. But what we do is we compare within each other. And it says here the standard deviation of the number of sales was 5, and the average was 87. So we found that the coefficient of variation, just simply dividing it out times by 100, is 5.7%. Is it widespread? Not too bad, right? Now if we look at the commissions now, it says the standard deviation is 773 with the average of 52.25. Divide those out times by 100, we get 14.8. Which one has a higher percentage of variation? Commissions. Commissions is more variable. So therefore, what it means to be more variable means more spread out. One person might be making more than the other person. Whereas in the number of sales, everybody's kind of selling the same amount of cars, right? 5.7 is not very spread out. Most of them are selling the same amount of cars, but they're making a lot of difference in money. Is the commission. That makes sense. Understand how the terms mean. It's a little different, okay, let me just look here. It's a little different than what we dealt with at high school. We get a little more into the theory part of it. Easy example to approximate standard deviation is just taking the range divided by 4. The easy way to say this is we don't use this. They say it kind of gets you close to the standard deviation to check if you're close. We do the standard deviation. This only works real well if your graph is bell-shaped. If it's not bell-shaped, if it's skewed, this is way off. And I'm not going to get into, I think the next thing is Chebyshev. I will deal with Chebyshev's theorem. Chebyshev's theorem. So this gets you through the basics of starting to do the standard deviations and variations, and then we'll talk about Chebyshev's theorem, and we should be able to finish that. Good. That's what we cards. I finished that. 3, 4. No, wait. Tomorrow we don't get up early. When is the activities tomorrow? 7, just 7.
There.